Hi everyone, welcome back to the channel. So today we have a different problem here. This is sent by one of our subscribers. And I think this is a pretty interesting problem and everyone should try it out. It seems pretty simple initially, but as you progress, you will find that there are more to it than meets the eye. So let's understand the problem first. Problem is that there is a cylinder here of radius r and there is a rope which is placed around the cylinder like this, half of the cylinder, and this rope is being held by two strings with tension T0 each. Okay, so T0 is the tension using which the rope is being pulled so that it is kept like this. And the question is, what is minimum T0? Okay, and the second question is, if I decrease the T0 by some small amount, let's say epsilon, which is very small, then at which point on the cylinder the rope will lose the contact first? That's it. Okay, so why don't you go ahead and give it a try? Okay, so how do we approach this problem? When you look at it initially, it seems that we just need to balance the tension with the weight of the rope. So 2T0 equal to weight of the rope. But that's not correct. Why it is not correct? Because the rope is being pulled by these two strings. Therefore, the cylinder is applying some normal force here on the rope. You see that? Since the rope is being pulled by the string. Therefore, these tension or the T0 should balance this normal force also. Therefore, we need to compute the normal force as well before we write the equation. Okay. So, if you understand this much, then the next question is, how do we approach this problem? What we should do is take a segment of the rope, let's say this segment, and analyze the forces here, and then use the Newton's law to balance those forces and figure out the answer. Let's say this is O and this is, let's say, the line which is going down, and at some point here, let's say a small segment of the rope. Okay, and rope is going to be curved because it is going around the cylinder. Okay, now let's say that this angle is theta. Okay, and the small angle that being subtended by the small part of the rope is, let's say, delta theta. Okay, so far so good. Let's call these points as A prime and B prime. Okay, and the center of this point, let's call it C prime. We will see why we are doing this. So if you see that there is a tension here which is being applied at this point A prime in this direction, because the rest of the rope before this is pulling this piece of the rope, small piece of the rope in this direction, and let's call this T. Okay, now this is perpendicular to this line because this is tangent at, this T is tangent at point A. Okay, similarly we have another force which is T plus, let's say, delta T. So delta T has been increased because we have added some mass here because of this segment. And this is also a tangent at point B prime. So there is a 90 degree with this line OB prime. Okay, now we need to pick one axis here so that we can balance the forces. So let's say that we pick the axis which is tangent to the midpoint of this rope. And it is convenient because both T plus delta T and T will make same angle with this line, and you will see how. So let's draw the line which is tangent at C prime. Okay, so let's say this is C prime. Now if this is delta theta, then what is the angle made by, let's say, if I join O to C prime? So this is going to be bisector here. So this means that this angle is delta theta by 2, and this is also delta theta by 2. If that is the case, then since this is 90 degree, so in this triangle OC prime B, okay, this is 90 degree, so this is 90 minus delta theta by 2, hence this angle is delta theta by 2, and this angle is also delta theta by 2. Okay, so far so good. So let's call this axis as x-axis, and perpendicular to x-axis, let's say this is y. So we place the y in this direction. Okay, so x and y. Okay, now we have something in place as far as the free body diagram is concerned. And where do you think the normal force is acting? So normal force, let's say, is acting at the center of mass, because this is so small that there is a normal force acting at the center of mass, and let's call it n. Let's say that the length of the segment for this rope is delta L, and this is nothing but r delta theta, because r is the radius of the cylinder. And what is the mass? Delta m mass for this particular length is going to be lambda, which is given as the mass density, into delta L, which is lambda r delta theta. Right? Okay, with these things in place, let's write the equation fx equal to max. Okay, in the x direction, we know that there is no acceleration, so this is 0. Okay, so what are the forces then? T plus delta t cos delta theta by 2 minus t cos delta theta by 2. And where is mg acting? So delta mg is downwards. And this angle is theta. So this angle will be 90 minus theta. So then minus delta mg sine theta should be 0. Okay. Now let's simplify this. So t cos theta by 2 will cancel out. So all we have is delta t cos delta theta by 2 equal to delta mg sine theta, right? Which is nothing but lambda r g sine theta delta theta. Now if delta theta tends to 0, okay, and delta t also tends to 0, then cos delta theta by 2 will be 1, right? And then instead of delta t, we can write dt equal to lambda r g sine theta d theta. And let's integrate from t1 to t2. Okay, t1 is the force at this point, and t2 is force at this point, which is equal to t0 as well. Okay, so and theta from 0 to pi by 2. I think this much should be clear. Then we have t2 minus t1 equal to lambda r g cos theta minus 0 to pi by 2, and therefore it will simply be lambda rg, right? So t2 then is nothing but t0 equal to t1 plus lambda rg. So this is our first equation. Let's call it A. Okay. We can write another equation in the y direction. So we can simply again say Fy is equal to may. And again, in the y direction also we have 0 acceleration. So then we can write, if this is the positive, then n is in opposite direction, so minus n. And then these t plus delta t will have a component in this direction. And since this is delta theta by 2, so this angle is 90 minus delta theta by 2. So t minus n plus t plus delta t sine delta theta by 2 plus t sine delta theta by 2 and minus delta mg cos theta. Okay. should be equal to 0. Okay, so which means n plus delta mg cos theta equal to 2t sine delta theta by 2, okay, plus delta t sine delta theta by 2. Now again same, delta theta is tending to 0, which means sine delta theta by 2 I can write as delta theta by 2, okay, and delta t into delta theta by 2, this part is going to be further small because both are very, very small. So this we can take it as 0. Okay. So then n plus, we can replace delta m with lambda r g cos theta delta theta equal to 2t sine delta theta by 2, which is 2t delta theta by 2. 2 will cancel out, and therefore it will be t delta theta. Therefore n is t minus lambda r g cos theta delta theta. Okay. Now we know that for rope to be held in this way, the n cannot be 0. So n must be greater than 0. Okay. That implies t minus lambda rg cos theta should be greater than 0. Therefore, t is greater than equal to lambda rg cos theta. Now, minimum t is going to be lambda rg cos theta. Now, at theta equal to 0, t minimum is nothing but t1, because theta equal to 0 is at this point. You get it? T minimum at theta equal to 0, you will get T1, right? Because T1 is the tension here at theta equal to 0, right? And at theta equal to pi by 2, we have T2. Okay. So T minimum is T1 at theta equal to 0. Therefore, T1 is lambda Rg. And hence, if we take this as equation B, then here from A and B, we get T2 or T0 equal to lambda Rg plus lambda Rg equal to 2 lambda Rg. So this is the answer. Okay. This is the answer. And if you just compare it with the, when cylinder, let's say, is absent and we just want to hold the rope with T0, then in that case, T0, let's say prime, will become simply the mass of the rope, which is pi r g, correct? Therefore, T0 prime in that case is, and lambda, don't forget the lambda, pi lambda rg by 2. Okay. If you compare this, let's say this is something, let's say C. If you compare C with this particular T0 expression, then 2 is greater than pi by 2, right? So this T0 is greater than T0 prime. And the difference that you have, that 2 minus pi by 2 Rg lambda, this is what is being there because of the normal force, because the cylinder is pressing the rope. So this is because of the cylinder pressing the rope. And in absence of cylinder, this is not there. So you get this answer. But in our case, this is the answer. Okay, this is the answer. Now, the second question was that what happens when I decrease the T0 little bit? So we know that T has to be greater than equal to lambda rg cos theta. This is maximum at theta equal to 0. So maximum at theta equal to 0. So when T0 goes a little bit below the original value, the value that it is required to hold this rope, then the force at the bottom, this is force at the bottom part. This will get disbalanced immediately because it required, T bottom required lambda Rg, and we just went below lambda Rg, a little bit below, and therefore the bottom part will get disturbed immediately because other could balance out because of the cos theta, because if theta is greater than 0, this expression goes down, right? So if you see the T bottom case with theta, so this is this something like this, right? So this is at point C and it keeps going down. It's a point B. And if the tension goes a little bit below the required, this part will get disturbed first, which is the bottom first. So I hope this is clear to you. And I also hope that you enjoyed this question and you learned few things. Thank you very much. Thanks for watching. Please do subscribe and like the video. Subscribe and gain access to concepts and tips for doing better in IIT, JEE or other examinations. Keep up the great work.